Okay, so what we have seen is that there are two diagrams, which is the S and T channel for 2 to 2 process, which don't violate any charge and color breaking minima. Color breaking, sorry, I'm using some which don't break charge, electric charge. And we also seen that this particular diagram doesn't work because it breaks electric charge. Meaning in the sense, when I say it violates electric charge conservation. Now, however, and I also mentioned that this is not going to arise because electric charge conservation means gauge invariance is a violation. Non-conservation means gauge invariance violation. So this diagram should not come in the Lagrangian. So let's write down. So okay. So so the next step would be, after drawing the diagrams, we have to see how much each diagram contributes to the amplitude. So if these are these two diagrams, so each diagram would contribute, each of these diagrams would contribute to the amplitude. So what we need to write down is the amplitude for each of these diagrams. Now, what is the rule? What are the rules for writing down the amplitude? So once we have written the Feynman diagrams, or drew the Feynman diagrams, the next step would be to write down the Feynman rules, meaning to write down the amplitudes corresponding to each of these Feynman diagrams. So the amplitudes are written, so the amplitudes can be written by using something called the Feynman rules. So if you just multiply, okay, so let's take one particular example. Okay, so the Feynman rule of, for example, take diagram A. So something like this. So E, 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 E. So the idea is that so the amplitude is nothing but multiplication of all the sort of wave functions, and it is essentially a multiplication of all the wave functions and the interaction. So like I said, this is free particles. Here it's free particle, here it is free particle, here it's a free particle, here in and out states are free particles. At the interaction, you multiply just all the free particle wave functions with the interaction strength and the propagator. So essentially use free interaction strength, propagator, then again interaction strength, then free states, which are essentially out states. Out. This is in. So these are in states, this and this. So say, let me mark them in some in states. I mark it within some blue color. Okay, so these are your in states, and the out states I mark them in green color. So this is your out states. Okay, so the in states comes, and there is an interaction here. So this is a current interaction. This is an in state and an outstate current interacting with a photon. Okay, this current is interacting with photon. Then there is a propagator, then an in-state and out-state current interacting again with a photon. And in these two currents are multiplied by the propagator, That's it. So this is as simple as writing the amplitude. Okay, so let's write it down. Let's list out all the rules first, so that we can write down all these wave functions in a second. Okay, so the first one would be incoming electron, okay, with an arrow like this. So this is given by u with the momentum p, and this is the wave function. No? So we start always with the vertex. So if it is incoming, what I mean is it is incoming to the interaction vertex. So this is the interaction vertex. Okay, now same thing if it is in outgoing. So from the vertex, if it is, okay, I drew it wrong. So if it is an outgoing particle, it is represented by u bar. Okay, incoming particle, this is outgoing particle. Incoming antiparticle, this has an opposite thing, v bar of ps. Incoming antiparticle, then outgoing antiparticle. Now if you see the main difference, okay, let's look at incoming particles. Say for example, for the incoming particle, you see the difference is two things. One, the sign of the arrow. So if you know the sign of the arrow is opposite to the direction of momentum, that is essentially an antiparticle. And if the sign of the arrow is towards the direction of the momentum, that is a particle. Similarly, an outgoing particle and its sign of on the propagator, on the wave function. Okay, so this is this arrow. This arrow of the outgoing particle is in the direction of the momentum, then it's a particle actually, which is multiplied with the u bar because it's an outgoing particle. Whereas for an antiparticle, the direction of the momentum and the what do you call the arrow on the external line, these are called external lines, is opposite to the direction of the momentum. So that way we know, we can keep track of what is a particle and antiparticle. So this arrow essentially denotes on the lines, okay, it denotes the flow of charge. Because we are in QED, this actually denotes the flow of electric charge. Okay, so everywhere always start with the vertex, and anything which comes in which is a particle, you have u of ps. If it is an antiparticle, you have v bar of ps. So it has the opposite, meaning you multiply with v bar. Anything which goes out from the vertex, outgoing, it's u bar, and the antiparticle would be just v. Okay, it has the arrow sign opposite to the direction of the momentum. Okay, so if you want to be more clear, p is in this direction for an incoming particle, so p is also here for an incoming antiparticle. Okay, so this should be clear to you. Now what about propagator? Okay, then the other important, once we have the interaction point. The interaction point or the vertex. So the vertex is given by, so this is time with a factor minus IE gamma mu. This is coming directly from the Lagrangian. Okay, now this, you see this one. So the vertex, if your time is like this, so the vertex always conserves electric charge. How do you know that? Okay, how do you know that it is always conserving the electric charge? Because you see, the arrow is always continuous. The arrow is always should be continuous, never in conflict with itself. So two arrows do not come opposite each other. Say for example, in the case we were planning to write an S channel of both electrons. If both of them are incoming electrons, you will have such an arrow in which there is no flow of electric charge. Here there is an extremely nice flow of electric charge which is continuous. Here the electric charge seems to be in conflict. They are sort of attacking each other, they are cancelling each other, or it's same electric charge, so they are joining. There is no electric charge conservation because there is no, they are attacking each other. Remember, the photon has no electric charge. Okay, the photon has no electric charge, unless if you have the photon to be doubly electric charge, this such kind of lines will not be allowed. So this is not allowed in the Lagrangian because the Lagrangian always has this kind of charge, this kind of thing. Okay, if the momentum is in this direction, this is one. So what happens in the antiparticle case? Also, it will be very similar. Actually, the vertex, it will be just like this. So in the antiparticle case also you will have, so the electric charge will be in this opposite direction, but it will always be a continuous flow of line. So anything like this or any vertex which is like this, these are not allowed. Okay, okay, in which there is a conflict. So this is one direction of electric charge, this is one direction of electric charge, it doesn't work. So the electric charge should be always continuous line. So in any of the Feynman diagram, the electric charge should always be continuous line so that it shows that it is conserved. So this is, both these diagrams not allowed, and not allowed by what? By the Lagrangian. Okay. So the Lagrangian doesn't, Lagrangian is written by assuming a conserved U1 symmetry which automatically has this property. Okay, so automatically you only get this kind of vertices. So these other kind of vertices will not appear. Okay, these other kind of vertices will not appear in the case of, you know, these will not appear essentially. These kind of vertices will not be appearing in, say for example, in QED, because they violate electric charge. Okay, so this is one thing. So the each vertex gives you a factor IE gamma mu, depending upon the words process and how the vertices. Now the most important point is propagators. This also these are the virtual particles. For the photon, so with mu, this is minus I eta mu q square. This is the momentum of the photon. And there are other factors. Meaning there are issues with gauge invariance and everything. Meaning gauge choice and everything. But okay, let's just for the starting point, we'll skip those things essentially. Okay, the next one would be the what do you call the propagator of the electron. So I think this also we have done. So the propagator of the electron is given by propagator of the electron is p slash, it is 1 by p slash minus m. So this is can be written in terms of you multiply p slash plus m and minus m on both on the top essentially. So this is represented by this. Okay, this has I say this is the momentum q, it is q slash minus mf. This is equal to I q slash plus mf by q square minus mf square. This is exactly the scalar propagator actually. So the Feynman rules, okay, let's write it down. We have written okay, we have to write incoming for two fantastic charged propagators. Then we have written the vertices. This is the vertices, so 2, this is 3, which is essentially propagators. So this is vertices. Then we wrote propagators for the photon and electron. We had to write the incoming electron, incoming photon and incoming okay. So the incoming, again starting with the vertex. So this is the incoming photon. What did I call it? 1A. So okay, one incoming photon. So this has a wave function epsilon mu. Okay, and the outgoing photon, because photon is its own antiparticle, is just epsilon mu star. Okay, did I miss something more? Any other Feynman rules? Okay, this will be fine. And then we are now sort of ready to write the amplitudes for some basic process. Okay, there are other things like anti-symmetrization over the spin states and stuff like that, averaging over the spins. We'll see. We will see it as we write it down more. Okay, as we go into more and more complicated scenarios studies actually. Okay, so let's again go back to our molar scattering. Now we know all the rules. Now let's try to apply them. Okay, we have seen the summary of the rules is essentially you have incoming and outgoing particles, vertex coefficients, and then propagators, and that's it. So we have, say, so there are two diagrams, E, 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 E. Then another diagram is okay. So we call this as U channel. This we are calling as a T channel. This is E, 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 E. So the electric charge is flowing like this. So let's start with diagram 1. So diagram, so this will, let's call the amplitude associated with this one is M1 and the amplitude associated with this two as M2. Now we want to compute M1. Okay, and the total amplitude is M1 plus M2. Okay, these two diagrams. Okay, so okay, we had to worry about the sign also between them, whether if we interchange the fermions, because they can pick up a minus sign because they have to be anti-symmetrized actually. If they are the same states, so in principle this just becomes a minus sign between these two states actually because of the anti-symmetrization. But okay, yeah, okay, because if you have two incoming or outgoing electrons, because they are same states, they are same fermions, so if you interchange them, you pick up a minus sign. Okay, I just take this rule as anti-symmetrization rule. I'm not going to okay, this I won't be able to say why this happens. Okay, this is just a way of keeping track that these are like fermions, meaning the same fermions here, meaning in both the process essentially. Okay. Okay, now let's go to the diagram M1. So okay, so this is, now let me assign the momentum also. Okay, okay, and then let's write it down. So first let me call this as P1, P2, and then I call this as P3, P4. So this would be Q. Now from energy momentum conservation at each vertex, I know that Q is equal to, okay, P3 minus P1, or it's equivalent actually, it's P1 minus P3. Okay, so Q square is equal to P1 minus P3 square. This is something I should I have in note. Okay, and this is also equivalent to P2 minus P4 whole square, just from energy momentum conservation. So now let's write down what would be the amplitude. The amplitude would be, now I want the amplitude, okay, typically the way we write it down is that we start with the external meaning outgoing particles. So outgoing particle in this case has a momenta p3. So you have u bar p3 s, then there is a vertex here, so that is minus I e gamma mu. Then there is a vertex here, there is a propagator incoming particle here, which is u of p1 s whole thing into. So this is this part of this thing essentially. Let me see if I can color it with something. So this part comes from this leg, okay. Comes from this leg. Oh, why is it coloring the entire thing? Okay, so let me just comes from this leg, okay. Then the second part, now these two, the other part comes from this part. So let me write down that. So that would be, this is all again electrons, but with opposite, with different momentum. So this would be u bar of p4s minus I e gamma mu, because it's the vertex which has an IE gamma factor, and then you have u of p2 and s, and the thing which, okay, I shouldn't put the same index, so I put it as mu, and the index which meaning these two, so this I'll color it with, say, green, and so this is the same green which appears here, and these two are connected by a propagator which is minus an eta mu by q square, and q square is again related to the total meaning p3 minus p1, p1 minus p3 whole square, and p2 minus p4 whole square, okay. So the total amplitude of this particular process, now you see it's so simple. So m1 we already got it, okay, is equal to u bar p3 of s, okay, minus okay, let me write down. So there are how many? 1, 2, 3, 3 i's, so 3 minus signs, so that is minus I cube, so that is minus plus I, so this will be some plus I, then e square, because there are two vertices, by q square, because I can take this out, q square, okay, eta mu I can absorb into the other one, so eta mu times gamma mu is equal to gamma nu, so this just becomes u bar p3 of s gamma mu u of p1 of s into u bar p4 of s gamma nu u of p2 of s. So your amplitude looks very simple and nice and cute. Okay, so this is your amplitude. Now you have to integrate over all possible internal momenta. So you have to, the actual amplitude m1 would be, because the internal amplitude is not a free parameter, it's sort of controlled by p3 and p1, at least in this case. But in other cases you'll have some internal amplitudes which are completely free, and they have to take okay, so p3, you have to integrate over all of them. Actually we'll see, meaning there in higher order perturbation theory that is possible. P1 minus P3 whole square times, it doesn't matter whether it's P1 minus P3 or P3 minus P4 or P1, so gamma mu u of P1 s u bar of P4 s gamma nu u of P2 s. Okay, now so we know that there is a phase space associated with this diagram, so which we have written in most general form. So now we also know how to write the amplitudes essentially. So we know for one diagram we have written the amplitude. The second diagram amplitude also, let's write it down. So second diagram would be wherever there is a so we can actually, we don't have to compute the entire thing again. It turns out that wherever if you exchange P3 with P4, you'll get back the same thing. So you'll have the second amplitude. Say for example the first term would be P4 u bar P4. Okay, let me write down, so you'll see again what I will say essentially. Okay, so this is the vertex, so this is let's just say this is also q square. Now this is P1, P2, this is P3, this is P4. So now I have the same vertex here, so I can write the amplitude m2 directly is equal to u bar P4 of s. Now q square is equal to what? P1 minus P4, that is equal to P2 minus P3. Okay, so now you see that this is u bar P4 of s minus IE gamma mu, the vertex factor, and then this is u of P1 of s, then okay, minus IE eta mu by q square, then you have u bar P3 of s minus IE gamma nu u of P2 of s. So this gives me now if you look at okay, let's simplify this and just make a comparison. So if you just do that comparison before doing, let's do the simplification. This gives me again I square by q square u bar P4 of s gamma mu u of P1 of s u bar P3 of s gamma nu u of p2 of s. Now compare this with m1. M1 is u bar p3 of s gamma mu u of p1 of s, p4 and p2. So this is p3 and p2. This is p4 and 2. So you get this amplitude if I exchange m1. Okay. So m1, if we exchange it where p3 goes to p4 and vice versa, it gives me m2. Okay. So if you exchange p3 and p4, you will get back m4 essentially, m2. There is a more generalization of these kind of things for 2-to-2 process, which is called crossing symmetry, but yeah. Now m1 and m2 have relative minus signs because I said if you have the same meaning. So these two diagrams just change by interchanging of these two incoming lines or outgoing. In this case, it's the outgoing lines I interchanged, right? These are the fermions which are interchanged by outgoing electrons or positrons, say for example. In this case, it's just electrons. So if I do that, I get a minus sign between this. So the total m1 minus m2. So the total m is equal to minus I square by q square, and of course the q square as such will change. Okay, so okay, one second, I just had to write it down. Here the q square, in this case m2 is p1 minus p4 square, say for example. So because this is equal to p1 minus p4 whole square, whereas in the case of m1 the q square is equal to p1 minus p3. So wherever there is a p3, you replace it by p4, and wherever there is p4, you replace it by p3, and you get back this amplitude. So this is m1 minus m1 with a substitution slash dot p3 interchange by p4. Now you understand what I have been saying so far, that these amplitudes, if I just follow an algorithmic approach, these are a bunch of rules which are given, okay, and then you can completely forget about the entire Feynman rules, Lagrangian, entire quantum field theory, Lagrangian, particle interpretation, everything, and just take this bunch of rules, okay, these bunch of rules. So first, of course, you have to draw all the possible Feynman diagrams, okay. So this possibility of these diagrams are also determined by this vertex lines, right? This is the vertex line. The vertex lines always save the electric charge, so they are always what do you call preserve the electric charge. They're always sort of conserving the electric charge. So they are conserving the symmetry, which is essentially the U1 symmetry. And so if you follow this thing, you know what are all the possible correct diagrams, and for each of these diagrams, just follow these rules, and you get back your amplitudes. So these are your amplitudes, okay. Now you have to further simplify them by using something called the trace tricks and other things. But okay, let's just so let's just understand how to write these things first, and then we can do that algebra of trace tricks and other things actually. Okay, so why don't we draw another process? Okay, we will consider all the process. I want to consider all the possible process and draw the amplitudes, write down the amplitudes for each of these process. So the kind of process we considered, I think I made a list of processes, no, somewhere. I'm just searching for it one second. Okay, so fine. Okay, let me write it down. So the most elementary set of process. So what we have seen. So these processes are essentially molar scattering, E minus going to E minus E minus. Now I want you to guys to look at what happens for E plus going to E plus E plus. Okay, what is this my amplitude? Okay, E plus going to, instead of electrons, what happens in the positrons? So this would be one of the assignments essentially. Say molar scattering with this thing. Okay, so let me go into the next set of scatterings, which is I'll put it up in the board, so don't worry, but I'm just announcing it already in the class. This will be a part of the assignment too. So now the second set of a thing would be Baba scattering. So let's do this one. This is E plus E minus going into E plus E minus. This also contains some diagrams which are called annihilation diagrams and some which are not. Okay. Now, if it has been a live class, I would have asked you guys to draw these diagrams. Okay, but anyway, since it's not live class, what are the Feynman diagrams? Contributing this process. Okay, so let's try to draw this diagram. So the first one would be, so let's take the time in this direction. So let's draw a vertex. So there could be an incoming electron and an outgoing positron. Okay, that is possible because the charge line is continuous. You cannot have two incoming electrons sitting in the same vertex. Okay, and coming in the same direction. So this is what. Okay, and then you can have the similar thing here. This is what an S-channel process. Out of all the process, you'll have, this is one of the diagrams. So this is what an incoming electron. This is a positron. This is an electron. This is a positron. This is an S-channel process. S-channel means you're adding up the momentum. Okay, this is again Q square, where this sum of this momenta will be added up. It's not the separation of the thing. Are there any other diagrams which are possible? So what about electron goes to electron, similar to the molar scattering? Electron, electron, and the, sorry, it should be a straight line, so but anyway, positron going to positron. Is this diagram allowed? Yes, this diagram is a T-channel diagram. And this diagram is perfectly allowed because the charge lines are continuous. So there is nothing which stops these charge lines. So along the fermion line, electric charge is always continuous. So as I said, it should either go like this or go like this. So both of them are fine essentially. So both these diagrams are valid. Now what happens if I exchange these two? Say for example, electron going to a positron, is there such a connection? No, it's not possible. electron interacting with a positron interacting with an electron, incoming positron interacting with an outgoing electron. No, it's not possible, because that would violate the electric charge, because in this case the charge lines are coming together. In the other case the charge lines are going opposite each other. Okay, so both these diagrams are allowed. So there are only two diagrams, S channel and T channel, and there is no U channel diagram for Baba scattering. Okay, so now I would stop here. Okay, and now I'll ask you two questions. What is the symmetry factor between these two diagrams? Okay, whether they should, because if I interchange two electrons, will there be, because there are two different particles, electrons and positrons. Okay, so do they add up, or do they sum up, or do they what do you call meaning do they what do you call get minus sign in between them? Okay, okay, so just think about this. Okay, the answer is that there is a minus sign, a relative sign between them. Finally, I also want you guys to write down this what do you call the amplitudes m for both these two diagrams. You can look at Zub or Griffiths or any of the list of books that I have given you. Okay, I'll stop here, lecture 14, and then we will see for the next lecture. We will continue with this, and we'll see a list of cast metrics. I won't go into the details. Most of that, I guess, you guys have to do it for homework, especially. Okay, and then we'll do the other two process which I have listed, essentially, which are pair production, pair annihilation, and a very very important process which is called the Compton effect. Okay, so let me stop here, and then we'll